Okay, so I wanted to talk, last time I was talking about classification. I wanted to talk about, finish talking about multi-class class. We talked about binary classification, how we could take examples of positive examples and negative examples, build a logistic regression problem, and then use gradient descent search to find the best separating line between them by that criteria. Now, classification tasks are not always binary. Okay, often there are a bunch of different classes that we might care about. Like when you classify a movie, often a movie by genre, a movie might be a comedy, it might be a drama, it might be an action movie, it might be a documentary. You can imagine that there is someone at Netflix whose job it is to somehow, given a movie, what genre is it, okay? And that would be, I claim, a multi-class classification. So now we kind of imagine a world that looks something like this. We've got, points, again, in feature space, but now instead of having 2 different labels, they can have 3 or more different kinds of labels. Okay? Any questions about that? Now, what is a bad idea in general to solving multi-class classification things? One idea might be to try to generalize the things that we did before, where we had a positive class weighted numbered 0, a negative class weighted 0, and a positive class labeled 1. And maybe we would represent every class by a different number, okay? And then maybe do regression or something like that to try to predict what the numbers were, okay? Now, I tried to convince you that regression would be a bad idea when you had 2 classes, okay? If you have a set of classes that are defined on some kind of an ordinal scale, it's not necessarily a terrible thing. If you wanted to try to predict how many stars a movie would have, okay, maybe based on you read the reviews or you look at the cast or something like that, you could say that there are 4-star movies, 3-star movies, 2-star movies, 1-star movies, and they're completely different beasts. The truth is that these classes, there is a linear ordering to them, right? And if there is a linear ordering to the classes, then we could kind of view the class identity as almost being like a numerical value, right? So if you have classes where the scales are ordinal, okay, like star ratings, like they call them Likert scales after the guy that I guess developed them, where you will try to predict if someone's going to completely agree with a question, completely disagree, or different stages between there. If you've got an ordinal scale on your classes, then it seems perfectly reasonable to represent them by numbers and try to predict a regression against them, right? But on the other hand, many things in life do not have ordinal scales among the classes. Let's think about hair color. Is hair color represented by a natural gradation, let's say, between light and dark? No. Some people might think about trivially that there might be, but I think the answer is clear that it's not, okay? You might say that on one end there's blonde, on one end there's black hair. Maybe here would be brown hair. But where would gray hair go on a scale like this? Okay, gray hair is a different beast, right? So if there is not a so either the classes are defined by just basically being numerical values, or there is not a, a linear order on the classes. If there is not a linear order on the classes, typically they are distinct beasts. And doing an encoding like this would be a bad thing. Any questions? Okay. Let everybody get settled in here. Okay. So what is the usual technique, best technique for building a multi-class classifier? The basic idea is to parlay our idea of binary classifiers to try to build, a set of binary classifiers where each one of them distinguishes members of the given class against all the other items. Does everybody see that? So here we've got three distinct classes in our problem. We can think about there now being three different binary class classifiers, and in the case here it's going to be trying to tell green things from non-green things, blue square things from non-blue square things, and red X things from non-red X things. Okay? Any questions? In principle, if you build such a binary classifier, okay, then set of binary classifiers, how would you identify which class a given item is in? Well, you could run all three classifiers, and for each one of these, in some sense, you're going to be getting a probability of it being a member of the chosen class. If the probability of it being in the chosen class green was 0.3, probability of it being in the the blue square class was 0.5, and the probability of it being in the red one was 0.4, we would classify it typically by picking the class that had the highest probability there. Any questions about that? Yes? But when you do this, one problem that we're going to come up with is that there's no reason why the sum of those probabilities should come out to 1. Okay, so let's think about what are the potential weaknesses of a scheme like that. One that is true is that you are not getting that the sum of the probabilities equals to 1, but you are still getting the sense that one of those numbers is going to be biggest. And so if you have to assign it one label without any further thought, picking the biggest is a reasonable choice. Why do you care if they don't sum to 1? The main reason is a question of confidence. I would say there's a couple of things. One is, if all you want to do is to get a label at the end, so you have to call it something, okay, it's a blue square, then I guess you don't need to know that. But if you want to know by how much, what is your confidence level, what probability is it of being a blue square, then this starts to become a meaningful thing. A dumb thing would be to say, oh look, when on the binary classifier it said that this had a 0.6 chance of being, in this binary classifier blue square came up 0.6, it would be a dumb thing to say therefore there's a 60% chance it is a blue square without normalizing it over this. We'll talk about, I know I talked about this before, but you have to normalize these probabilities to get something that is a reasonable probability. Okay? Any questions about that? Okay? Any other problems that come up with this scheme that people can think about? Okay? So, or challenges or difficulties or anything like that? Am I training too many times? I don't know if it's training too many times. It's if you've bothered to give me m different classes, I don't see it being a big problem to train m classifiers. Okay, but so I don't think that's necessarily a problem. Okay, any other ideas of issues? Okay, again, there's going to be. In general, the problem is going to get harder as you add more classes. This is one thing that needs to be seen. And again, I'll talk about that now. But one example of in a subtle way as to why things get harder in a, when you have multiple classes. What do we want the size of these training sets to be? We want them to be the same, right? So you want 1/3 of the things to be green, 1/3 of the things to be red, 1/3 of the things to be blue, right? What happens when we do the one versus all classifier now that we've done that? Do we still have the property that they're balanced? What if two classes have the same probability? The honest person would say, I can't tell, right? So if you're telling me that I try to classify and it's just as likely to be green and blue, sometimes, depends what you want to do, but I would think the honest thing usually is to say it's a tie, and I don't know. Okay? So I mean, in principle, these are numerical functions returning probabilities, and so if real numbers are very unlikely to equal each other exactly, Okay, so I generally wouldn't be worrying about the probability of being a tie. Okay, but I would worry about probabilities being close enough that I'm asked to make a pretty firm decision. Darn it, it's in this class, when there's not really that much of a, a difference. You came in when I was hitting around here before me was saying, oh, why did Nate Silver do such a lousy job, okay, on the election? And I said, no, I think Nate Silver happened to have done a very good job on the election. What did Nate Silver predict? He said that Hillary had a 71% chance of winning, okay, but Trump had a 29% chance of winning. Trump's chances of winning by Nate Silver were wildly higher than on any of the other sites, okay? When you look at the difference in the election, okay, Nate Silver said Hillary was going to win the popular vote by 3%, and she won the popular vote by 1.6%, okay? Is that a major failing or not? It's, in terms of the outcome of, if all you care about is the class label of who was the winner or who wasn't, then obviously it's a disastrous, prediction. But on the other hand, if it's a prediction with which we're saying, I really don't know very well, okay, it is not such a disastrous prediction. And that's why I think knowing what the probabilities, the confidence levels of your classification are very important. Okay? Any questions? I think you probably, if you watched the videos from the projects last year, you got a misleading impact on that because everyone there was determined to make a prediction one way or another on a discrete event. But obviously the sensible projects are what is the probability that this, how confident am I about this prediction? And you need to have a sense of that. Yeah?
Oh, no, I wasn't raising my hand.
No, behind you, though, somebody was. Yeah.
So we have like 3 classes.
Yeah.
And when we split them into a binary classification problem, we have like 2/3 of the data that is against.
Yeah.
So to overcome that, do we just take half of that data and train?
So the question of what do you do there, again, there's different ways you can think about it. One notion is to notice that if you had equal numbers of elements in the first class of every class to start with, then you have equal numbers against it in the other one, right? So if every one of them had exactly 1/3 of the elements, in all of these 3 classifiers, it's always 1/3 against 2/3. It's still kind of a fair contest, right? Where if these things were different in count, it would be a bigger problem. If all you're doing is comparing them against each other, arguably, so long as you're keeping the counts the same, they all have an equal chance of doing well. But again, if you have enough members of the class variable, of the in-class thing, it might be better to randomly throw out enough of the other elements to make it a balanced class. It depends what you're... That would probably be true even more so if you had a large number of classes, because then the imbalance would get very huge. Any questions? Okay, good. So what are the difficulties of having classes? The important thing is that multi-class classification gets much harder as the number of classes increase. If there are k classes, the monkey is right only 1/k of the time. Okay? And there's some other issues that come up with properly thinking about multi-class classification that puts a little bit of, that we have to think through whether we really want to do multi-class classification the way I was saying to do it. One problem is that when you have a lot of different classes, it's often the case that certain mistakes are more acceptable than other mistakes, right? So if I am, having an object classifier, if identify, a man as a woman, that's less of a mistake than if I identify a man as a plant. Okay, does everybody kind of get that? So you could imagine the fact that certain mistakes are more acceptable than others. Okay, and if you have a large number of classes, the probability you get the right class becomes very, very small. It's often the case that you want to get something that's at least close to the right class. Any questions? The other thing that happens is that when you have a large number of classes, it's often the case that the real population of the smallest class becomes very small. So let's say you wanted to predict what country people are from. Okay, how many countries are there in the world? 200. 200, okay? And what's the probability that when you pick someone off at random, they're from Malta?
1 by 250.
Well, 1 by 250 that they are, that the class would be Malta if the population of people of all countries were equal.
Yeah.
But the trouble is that classes tend to have skewed probabilities. Does everybody kind of get that idea? And, you know, you may work very hard to have a data set where you have an equal number of members from each class, but that's not the same as saying that it's equally likely that every label should be called. Does everybody kind of get that idea? As you have more and more classes, it's usually the case that the smallest of your class becomes vanishingly small chance of occurring. But if you're assigning labels according to the monkey, that class is going to be used far more often, objects are going to be labeled that way far more often than they should. So these are two different problems we've got to worry about with multi-class classification. Any questions? Okay. So what can I do to try to avoid the problem, to try to make it so that my mistakes in a multi-class problem are reasonable mistakes? Okay. It is usually better to classify your classes. If you really have a large number of classes, it often makes sense to kind of cluster your classes into comparable groups to kind of build a hierarchy on them so that you can first level try to predict which of the top level categories is it, and then keep refining as I go down the tree. Does this kind of make sense? That, you know, in the ImageNet, there's a very famous competition to try to do image recognition, what object recognition in images. And, you know, in this thing, they have millions of images you can train on. They have 21,000 different categories of items that could be the thing in your image. If you ask me for any given image, are you going to get the object right? I'd like to think the answer is no. The monkey has a chance of 1 in 20,000, right? You know, if I asked you guys to classify, you know, everybody right now, what do I wear? What did I come in here wearing? See this thing? Okay, everybody classify what this is in your head. Okay, now, what do you think this was? Jacket. How many people called it a jacket? How many people called it something else? What do you call it? A leather jacket. Okay, so there might be a leather jacket thing. Was there anybody who called it anything else? Okay, maybe it wasn't such an impressive demo. But does everybody agree that if you have a large number of categories, the odds that, you know, it's usually ambiguous where exactly it really goes, okay? And, you know, to maximize the chances you get something right, if you build a hierarchy on these things, okay? Then the first step is which of the bigger subgroups is it that my object is in. So ImageNet had like 27 top-level categories. Is it an animal, an appliance? Is it food? Is it furniture? You know, if you get the top level right, you're less likely to be embarrassed than if you don't get the top level right, right? And once you know, and getting the top level right seems like a much more tractable problem than getting exactly right this other categories. Any questions? So if you have a hierarchical problem with enough categories, you should definitely be using some kind of a hierarchy to help you, you know, you should cluster the categories together so that, you know, you make your problem simpler at each step. Any questions? Okay, so that should be clear. Yeah.
Like, can we use just simply a clustering algorithm, like with number of clusters equal to 21,841?
So one possibility, you're saying, oh boy, you know, you're going to talk about clustering in the next class, okay? Why don't we use some automatic clustering category on these things to try to group the categories by similarity? And that you might be able to do. But notice that if you took the 21, let's say you had 21,000 image categories, and you now did an automatic clustering, what is the name of a cluster that contains, let's say, that leather jacket? What's the name of the cluster that's going to contain leather jacket? Well, that's if you had somebody build the clustering. But if you automatically learned what the clustering was by, let's say, grouping similar things, images that look picture, it's not at all clear to me. You don't have a name for what that cluster is. Does everybody see it? You very well might put your clustering algorithm might put the leather jacket next to the rock, in the same category as the rock star, because these guys tend to wear leather, or motorcycle gang members, right? Because they tend to wear these things, right? So what I would say is that there is an advantage often, if you know enough about your domain to build a taxonomy that you care about. I think that is generally more useful than just doing a clustering. If you don't know anything, then maybe doing a clustering is a good thing, okay? But I am a big fan of taxonomies, okay? Any questions? Because you would like to be able to get this thing right as a piece of clothing, right? That's kind of, I think, your first order. If you have it as a piece of clothing, you're in reasonably good shape. Any questions? Okay. The other issue is that, when you build a classifier on a large number of groups, okay, it's very, very hard to avoid domination by rare classes. So at one point, my students and I were trying to build a classifier to try to identify the profession of people based on their Wikipedia page. That was kind of one of the things that we were trying to do. And one thing that you find is that there are, what kind of people are there in Wikipedia? There are, athletes, there are scientists, if you build 200 of them, you start getting to certain rare categories. Rock stars was one of these rare categories, okay? And what was the property? There are very few rock stars in the world. A very small percentage of Wikipedia is devoted to rock stars. But they are, in some sense, fairly distinctive in how they look and the amount of data that's about them. If you have 200 classes in the hierarchy, 1 out of every 200 people is likely to be classified as a rock star, okay, just a priori, just because that label is there. And so it is important to have some idea of a prior distribution. If you have a multi-class problem, this is a very, very important thing. Usually you know something about the relative rareness or scarcity of the objects that you're looking for, okay? And if you do, then this gives you a, you need to have, if, in fact, you have a classifier that has a tendency to classify things as rock stars a lot, okay? You would really like to use something like Bayes' law, okay? Bayes' rule, how would we interpret it? It's something like, what is the probability that someone is a rock star given that we classified them as a rock star, right? That's kind of one thing that we're doing. And one of the things that we're weighing for is, what's the probability that a person outside in the world is a rock star? And what is the probability that our classifier calls things rock stars? If you run it on a large number of pages and you find that it calls this class a lot more often, you would not want to assign that label as often as it is. You want to weigh it according to the prior. Any questions here? Okay, so these are two aspects that become very important in dealing with multi-class classification. Okay, these issues arise in binary classification, but they get exacerbated as you have more and more classes. Any questions?
So, what did this slide suggest to use Bayesian?
Well, it says that if you have ever are in a project where you're trying to say, oh look, my job is I work for Amazon, and my job is to try to figure out, given this book, which type of book is it. If there are 200 genres of books and you train on them, you had better know something about roughly how many books of each genre there are. Okay, because in the rarest genres, okay, there are going to be very, very few books. but classifiers are often liable to, to call it that more often than, if there's 200 labels you can assign, if you train it on equal numbers of these things, in principle, you want your classifier to return each class equally often. Okay? If you go to Amazon and one of the types of books, what is a rare genre of book? What would be a very rare genre of book that Amazon would? Cyberpunk, okay, let's say cyberpunk maybe. I think there's probably rarer things, What would be a rarer thing? Plays, for example. Some are written plays. Cyberpunk plays. You could imagine that some of them are books on religion. Books on philosophy is probably one that's fairly small, right? Bottom line is that there's no question that fiction is going to be a bigger component to the bookstore than philosophy or cyberpunk, anime or whatever that thing is. The important point is, if you don't have an estimate of the prior probabilities, you're almost certainly going to overstate rare categories and understate, popular categories. Any questions?
So like how can I use this if I know that there are certain categories that are...
Well, that's really what Bayes' law is. It's sort of about what's the probability that I should classify this given this evidence. Okay? And this was the probability that maybe you would have classified it according to your classifier. And this is what's the probability that it was a member of this given that classifier. But my claim is that Bayes' law gives you a way of incorporating how does your opinion change given more evidence. And given the fact that something occurs, infrequently, it should lower your confidence level when you issue a classifier that didn't know about what the prior was. Okay? This should be clear, that somehow that, when you look at, when a doctor is trying to do diseases, he's trying to diagnose your disease, you come in, you say, oh, I've got a stomach ache and I've got, he could say, you've got stomach cancer, okay? But he knows most of the time it is something else, right? And they're reluctant to call stomach cancer, okay, because there's other things that are more likely to be the case, right? And so your doctor definitely has a sense of prior distributions, okay, of what kind of things are likely to come in. Yeah?
Isn't this going to change like the more number of elements that you classify? It might be the scenario that your prior might get reversed, right? Like initially when you started out and when you classified like a lot more things.
Okay, so the way I think about it is there are, training examples. Recognize that there is a difference between the training examples you were given, potentially a difference between the training examples you were given and the universe of objects you're going to apply your classifier to. Does everybody see that? If somebody's job is, I've got to find pictures of 200 people from every country of the world so I can build a nationality classifier, you will have 200 pictures from every country in the world, including Malta, okay, and the Vatican City, okay, and you're going to, get a 1 in 200 chance of guessing if what country it is. But if later on you're applying it to pictures on Facebook, okay, it is no longer true that 1 out of every 200 people are from Malta. Does everybody see that? And that, if you've changed your distribution, it should be clear that if you know something about what the underlying distribution is, you have to be pretty confident before you declare somebody to be from Malta. Isn't that right? Okay? Whereas you don't have to be that confident to declare someone from China. 1 out of every 6 people in the country's from China, right? In the world's from China, right? So understanding what that prior distribution is necessary to make honest guesses at these things.
As you said yourself that we don't know the exact whole population, right? We just know the training sample, so it's quite difficult to estimate the right value of probability.
Okay. What you said, the question is, how do you estimate these things? I said, have honest estimates. Yeah. Okay. If if somebody gave you these training examples, you've got to ask them, what is the real population in the world? Where are you going to be applying this classifier? And if not, I can guarantee you're going to overstate unrepresented classes, right? Any questions? So this should seem like a logic thing. I agree with you. Where do you get it? Well, the point being is that if it's going to be a very skewed distribution, if you don't get it, you're going to be in trouble. Okay? Any questions? Okay, so that should be clear. And I think the final thing I wanted to say here was, again, this question of if you have binary classifiers that were independent, as we said, there is no reason why these probabilities should sum to 1. If you want to get real probabilities, what I would say is sum up for your particular item, what is the probability of it being a member of each class according to each of these classifiers. Let that be T, and then the probability of the element actually being in that class is going to be basically the probability recorded by the classifier for class C divided by this total. Any questions? And if you do that, then when you sum up these probabilities over all the classes, they will sum to 1. Any questions? Any other issues about multi-class classification? Yes, f of I is what's spit out by the classifier for class I on item X.
So you're looking at membership of a particular item into many classes and then dividing it by the total probability.
Right. So if there are C different classes, and I've got C different one against all classifiers, if f sub I of X is the probability that the ith classifier says that X is in class I, then T is the sum of these things. This is not necessarily equal to 1. It presumably isn't equal to 1. But if you then reinterpret the probability of X being in class C as being the value returned by the classifier divided by this sum, when we sum this up over all different classes, the probabilities here will sum to 1. Okay?
But again, now when you are looking at membership of a particular item into classes, one item will have a greater membership in one class than the others, right?
Yeah.
Then why is it important for me to even do all of this?
Well, there's a question of, again, suppose, let's say I wanted to put you in, there were 200 different classes, okay? I wanted to try to classify what country you're from, right? And suppose I could figure out who here looks like they're not from a particular country. I don't know if I can take a guess. But anyway, that doesn't make, if I pick somebody and if I told you that the probability of, it's one thing if we feel that there's a 0.7 chance of you being from that country. That's pretty good, right? But if there were 200 equally likely countries, what's the probability that it would be? 0.005, I believe, right? That's 1 out of 200, right? Suppose that the country which had the biggest probability had a probability of 0.006, right? We would declare you as being from that country. But that woefully underrepresents the right situation, right? We don't have very much margin here. Does everybody see that our preference for you being from that country as opposed to every other country is very, very small? Knowing the degree to which, what our confidence is seems like an important part of any kind of a classification problem, especially when you've got a hard problem with many, many classes, okay? So, yes, you'd like to return what is the most likely class, but you'd also like to return how confident are you of this. And this P of C is the probability of that you're assigning to it actually being in that class. Any questions about, yeah?
That T will be not equal to 1. I agree, but I want to know that whether T will be constant for different I or not.
T is going to be constant for all different I. I here is the class number, or the class ID, right? So in this case, C is equal to 200, and I equals 1 is equal to the United States. I equals 2 equals India. I equals 3 is China. I equals 4 is Malta, right?
I want to ask for different X, sorry.
What?
Different X.
So the X should be an argument. It should be PC of X comma C. I should have an X in here, okay, also, if that makes you feel better, okay? But the important point is that when I divide my pseudo probability from here by T, I get a real probability. Okay? Any questions? Yeah.
So the sum t should be lesser than 1, right? That is how you will be able to.
The sum of t could be less than 1, or it could be greater than 1.
But like then the earlier example that we took, like if it is 0.006 and the
Let's imagine we had a yes man classifying technology. That when I took a look at you, said, what's the probability you're from India? 0.8. What's the probability you're from China? 0.7. What's the probability you're from Israel? Hava Nagila, right? Does everybody see what we could do? There's no reason why the individual class classifiers can't all return high probabilities, right? Which class should we say you are? We should say you're from this class. What is the probability of that? Well, when we add this thing up, this looks to me like, what does this add up to? Somebody with a calculator. This looks like this is 0.7. Let's make this 0.7 just so I can add it up easily, right? This is 2.8. Now it's 0.8 over 2.8. What's 0.8 over 2.8? Someone with a calculator. Okay. This is not going to be, okay. What? Somebody having that number? 0.34. Okay, I'm hearing 0.34. Let's say that's right. What does this say? This says, wow, that guy's from India. This says, you know, maybe I'm not so sure he's from India, right? And there's no reason why the classifiers can't return numbers like this. There's no reason why t has to be less than 1. There's no reason why t has to be greater than 1.
So that is what I was trying to say, that this has actually made like our decision making ability is like further constrained, like rather than giving us a clearer answer.
No, this has made clear to me that yes, the majority class was from India, but are we very confident about our decision? The answer is no. Okay? Does that clarify, does that make your thought process less clear? If I said you were from 100% from India, yes, that would make it very clear, but would also make it very wrong, right? So we would want, you know, so knowing, having a sense of what our real confidence here seems like an important thing. And just looking at this individual thing from the binary classifier tells you nothing. All these values were relatively close together. Well, no, but it's a question of interpretation. If you read these things and said, the classifier saying the guy was from India said there was a 0.8 chance he's from India, then you feel, I got an Indian, right? When you said, when I looked over for all the classes, there was a 0.34 chance, 34% chance he was from India. Saying, well, I'm not really sure, right? Which of those is right? Well, you know, both of them are true statements, but the more meaningful statement is this one. Okay? Yeah.
Confidence is just a synonym for probability, right?
So here, again, there's a technical term in statistics of confidence intervals and things like that, and I don't want to delve into this. But what I will say that probability is a, you know, as we're using here, is certainly measuring some notion of confidence. How good do we feel about our selection, right? That's, I guess, the level on which I'm talking about it, okay? Any questions? There is a thing in statistics called confidence intervals, which is really a firm notion of what's the probability something is in a certain bound, and that's not what we're talking about. But we are talking about trying to get some kind of a measure of how strongly do we believe it. This would have given you a false measure of how you believe it. This would give you a more meaningful measure.
So in a nutshell, the value PC gives me the probability of any item lying in a particular class.
This should have, but recognize that this should have a second argument. If someone wants to email me and remind me to fix it, it should be PC of x comma c. Okay? So you should see that there's an x there. Okay? But it's basically saying, what is the probability that this item is from this class? Well, it's still a way of thinking. What's the probability the item is from this class? It's got to be, if it's a probability, implicitly it has to take into account the other classes. Okay? So probability should take into account the other classes. Okay? Any questions here? Okay, good. Any other question about multi-class classification before I move on? Okay, spent a little more time here than I thought, but that doesn't make you a bad person, people. Okay, let's go back here. Where did I go? Unfortunately, I'm loaded in a different place than I usually am. Let's try. So let me try this thing. Boom. 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 And boom. Okay. Any questions? So at this point, what I'd like to do is to shift gears a little bit and talk about nearest neighbor methods. Okay, we're still going to be talking about mostly classification, but it's a different kind of an approach to classification that I find actually quite useful and quite powerful and quite simple and quite interpretable. So I think nearest neighbor methods are very good things, and they're going to be getting into issues related to classification. So what is the idea in nearest neighbor classification? Basically, suppose we have a bunch of training examples, and we know that some of these are from class 1 and some of these are from class 2. Okay? What a nearest neighbor method is going to do is to say that when I give a new item, okay, a new query point, and I want to know, is this item red or blue? What I am going to do is to look at all the training examples and find which training example was closest to me, and then take the label of the item that is closest to me. Okay? Any questions about that? So if we assume that, again, as in typical things, we have a bunch of things that are labeled as positive items, a bunch of things that are labeled as negative items. I have a new query point that I would like to do. I compare me to all the training examples. Compute a distance between the new point and that training example. Once I find which one of those training examples was closest, just take the label from that. Any questions about that? Okay. So nearest neighbor methods have a bunch of good properties to it. One is that it is a very simple idea. Okay. In principle, you know, just nearest neighbor search, just distance things. 2, the results are very interpretable. Do you know why you give somebody a decision? If I classify you as being a turnip, why would I say you're a turnip? Well, I would be able to point to some turnip and said, this turnip looks like you, right? Okay, maybe the turnip had a beard. Maybe the turnip was wearing a jacket. Maybe something like that. Does everybody see that it's somehow explainable? I don't think you look like a turnip. Don't let me, no, nothing personal there. But is everybody going to get that idea? Many of the other cases, there's no obvious way to explain. If you look back and say that decision was bad, why did it happen? The other thing to note is that this simple method of nearest neighbor classification gives you nonlinear boundaries. If you look at this thing, why is it, if you look at it, is that boundary a straight line? It is not a straight line. And why is it not a straight line? Well, it is not defined by lines, or not, you know, except very, very locally. There's not linear hunks between it. So this here, okay, what's this thing here? This here is a nearest neighbor classifier where, let's say that we had blue points and red points given by these dots. Okay, these dots are, or let's say men and women. Let's say this probably is men and women, with the colors probably wrong, okay, in height and weight space. Let's think about it that way. Okay, if this was height, if this was weight, every man would be a point in space. Every woman would be a point in space. Does everybody see it? Now somebody else comes along with a new height and weight, and I've got to decide, is this a man or a woman? How would I do it? Well, I go through all my examples, and I find which is the input training example which was most similar to me, nearest to me, and I give it the same label as that. If the person with most similar height and weight to me is a boy, then I am probably a boy. And if the person that is of most similar height and weight to me is a girl, that person is I am probably a girl. Any questions about that? That is the philosophy here. But as we notice here, if you look at the boundary here, the boundary is not a single straight line like it was in, let's say, linear logistic regression or, something like that. Instead, actually, it really is, in this case, a piecewise linear function, okay, or a piecewise, depending on how you did, there's different variations, but basically it consists of a lot of pieces jigging and jagging between two things, okay? And therefore, the decision boundary can now get nonlinear, okay, and it can give you a richer potential explanation than one of these simple straight line things. Any questions? Okay? And if you believe that, the key issue to making, there's a couple of issues in building nearest neighbor classifiers. The key issue is, how do we find what the right notion of distance is between the points, right? Ultimately, we want to have a function that, given a training point and an input point, we want to measure a distance between them. Okay, what is the right notion of distance that we should use? Any questions? So, when people think about distances, when we think about distances in a geometric sense, we have certain properties of distances that we expect distances to satisfy. Okay, if I measure how far apart am I from you, if I look at it, we're probably about 10 feet, something like that, right? If you have a distance measure, typically we expect the following properties. Okay, we expect that distances are always positive. Does everybody kind of get that idea? Distances are symmetric. I am as far from you as you are from me. Distances are 0 if and only if the points are the same, exactly the same. Okay? And we also expect the notion of the triangle inequality, that the distance from me to you plus you to him is going to be greater than or equal to the distance directly to him. This is an as the crow fly properties, right? The shortest path between two things should be a straight line. So if you instead try to go through a point Z, you can't make the tour shorter. Okay, if Z happens to lie on the line between us, the distance can be, some of the distances can be the same. Any questions about that? So any measure that satisfies all four of these properties we call a metric. And we are used to thinking about, our notion of geometry is built around Euclidean distance, which happens to be a metric. And so all of our intuitions about distances assume that our notion of distance is a metric. Okay? If your notion of distance is a metric, you can use that intuition. If not, potentially weird things happen. Any questions? That said, many of the similarity metrics that one might naturally use are not metrics. When we talk about the correlation coefficient, right? You could imagine if you have a vector, you have a row of features. You could imagine, how similar am I to you? How does my feature vector correlate with your feature vector, right? This is like a dot product, or this is a cosine similarity, or its coefficient. These things go from -1 to 1. Does everybody see that? So correlation coefficient is a measure of similarity, but it is not a distance, it doesn't satisfy the distance metric properties. Any questions? Does that mean that you can't use correlation to figure out which is the most similar thing? No. But it does mean that if you're working in a high number of dimensions, you don't understand the geometry the way that you should. Okay? Any questions? Other measures that are not, there's often a lot of distance measures that are not symmetric. Okay, some of these mutual information measures, given my probability distribution, how far am I from another probability distribution? These things are often not symmetric. Okay? And if you have a non-symmetric notion of distance, that's also a weird thing. You don't know how to think about that very well. Any questions? As an yeah.
Claim here that when we have like high number of features in a vector, we should probably go for distance function.
I'm not really saying that a high number of features go like that. I am saying that recognize that certain things are distance metrics, and certain things aren't. Okay? So for example, we'll talk later on about data structures for finding nearest neighbors. These work in worlds where often, if it's a metric, they know the space is laid out in a way that you can find nearest neighbors more efficiently than searching through all possibilities. It would be hard for me to build a data structure, given a point, find which other one has the highest correlation with me. But it's easy to build relatively easy to build a data structure such that I can more quickly find which is the nearest point according to a distance metric. Okay? So the important thing is to be aware, I would say. Do I say that you can't use correlation for solving nearest neighbor problems? The answer is no. Okay? Do I recognize that there might be weirdnesses here? Yes. Okay? Do I recognize that there's limits in how you can, what kind of data structures you can build? Yes. Okay? Any questions?
When we're dealing with suppose categorical data, like class labels, something
Yeah.
like that, then I think it's more logical to use similarity or coefficient and compare to simple distance function maybe.
Well, you're saying one of these might be better than that. I'm not going to even argue which is better. I'm going to argue that they are different, okay? And that you should be aware of what you are using, okay?
And so I feel it's like one problem, like many times, like if we're having a data which has some numerical values and some categorical variables,
Yeah.
then how do we find the distance between two different labels?
Okay. So how do you find the distance between things? Let's say that you have a vector that says that there's somebody who is, got a height. You've got their height, their weight, their gender, right? You're telling me that this person is of height 6.3, their weight is 180, they're male. What is the distance between one of these and one of those? Okay? And what is clear is, in order to reduce it to a distance, you need to find some kind of a number that would represent what that difference is. Okay? And what you're right in thinking about is that if you're trying to measure the distance between these records, when you don't have all numerical values, there is a problem here. Okay, so everybody kind of see that if you have a record that is of mixed numbers and categorical features, if you want to find the nearest neighbor here, you need to find some way to weigh what is the distance between an M and an F. Okay? And that probably requires knowing something about your domain. But we agree that that's a problem that you got to deal with if you're going to do this. And it's not clear that problem doesn't go away if you use correlation.
Yeah, in this case.
Okay? But recognize that the real problem is that when you've got non-numerical data, computing what the difference between them is an ad hoc thing. Yeah?
I think I missed it. What's the example?
The example is, let's say I am trying to hire, again, this is not the best way to hire people, okay? But let's say that I was trying to find, no, it's not a good way to hire people at all. But let's say that I was trying to identify which people are most similar. Okay, you could imagine between, if I had records on each one of you in here, it's perfectly fair to say who is most similar to you in the class, right? And some of those features might be things like height and weight that are numerical, and some of those things are going to be categorical information, like gender, like hair color, like things like this, right? And now, if I'm going to try to use a nearest neighbor thing to say who is your nearest neighbor, implicitly I've got to know how much of a difference is it that we differ in that categorical field, right? You've got to have a way of reducing that to a number. And this is probably a domain-specific problem rather than an absolute thing. Yeah?
Is it enough to just ascribe different
you might say, you might encode it as 0, 1, okay? But, you know, as we will see, there's going to be there's several different issues when it comes to encoding numbers to compute distances on it. One of them, let's say we agree class labels. Everybody see that class labels are a problem. And you may want to say, okay, I'll solve this problem by calling it 0 and 1, right? Does that solve your problem? Well, now they're numbers. But is there another problem here?
But now the computed distance, I mean, if you compute this, like example 0 and 1, that will add an unnecessary distance of 1 to my overall answer, which has got no meaning.
Well, you're saying that if the gender didn't matter, then if I include this distance, it's going to add something. Well, I'm assuming here it does matter. But what's the bigger problem, yeah?
Difference of 1 point in height is going to overpower the difference.
Does everybody see that the difference in height from 180 centimeters to 179 centimeters is exactly as big as the difference from male to female?
That we can normalize, I guess.
Okay, so that recognize that that's a problem here. This is a big question about why we normalize things. Does everybody see that? So the problem here is not can we give it 0, 1? The answer is yes. But we need to make sure also when we do this that the scale of these things are comparable. If you want the features to be of comparable power in making this decision, these numbers have to be on the same scale. What would be a way we could make those numbers on the same scale? Z-scores. Does everybody agree if we did Z-scores? Now, then we've got three things that are arguably they're all the same mean. They're all the same variance, say standard deviation, right? Now you're probably going to get a more meaningful thing if all the features are of equal importance, okay, than if you use the unnormalized values. Any question?
One more problem here, that if we have more than 2 classes, suppose.
Yeah?
If we have more than 2 classes, then they might be 0, 1, 2, 3, something like that.
Right, so now let's look at hair color. And we've got blondes, we've got, we've got black hair, we've got gray. Okay?
In this case, we will assume that one class is near to, like much more closer to 1 than like some other. Is not the case.
So one possibility is you could say that, that two things are going to be the same. They're distance 0 in this field if they agree with each other. They're distance 1 if they don't agree with each other. That might be one way to measure what the distance is, right? If we say that if you're in the same group, one common way to deal with it would be to say that if you're in the same group, the distance between us in this field is 0. If you're in a different group, the distance is 1. Or if you know something about the relative closeness of the groups, right? You might very well, use a distance measure that reflects the closeness of groups. Remember when I was talking about the hierarchy here? Suppose I had a hierarchy of groups. Do we believe that this group and this group are closer than this group and either of those groups in that group? Yeah. What would be a measure of distance that might reflect that? Maybe the distance in the hierarchy. Does everybody see that? That was 1, 2, 3, 4 steps, and this was 1, 2, 3, 4, 5, 6 steps, right? So we recognize that when we're doing these things, there are complications. Does everybody kind of see that? And if you don't think these through, you end up with nonsense. That is what I want you to say. Nearest neighbor search is easy if you have thought through your data in a sensible way. Okay, if you haven't thought this through and do this in a sensible way, you will end up with comparisons that are meaningless. That is the big picture question. Any questions? Okay. We'll get back to that a little bit later, I think, but let me just go back and do it again. So we talked about distance metrics. What is everybody's favorite distance metric? Okay, it is the Euclidean metric, where basically we take the square root of the sum of square differences between things. If we have 2 points in d dimensions, we sum up for point x, the value in the ith dimension minus the value for the point y in the ith dimension. square it, and the sum of squares. Any questions about it? That is the Euclidean distance metric, okay, which we learned to love. And that satisfies all the properties that we had been talking about. Now, an important thing to see is that we can generalize this notion of Euclidean distance metric to a bigger class of metrics called LK distances, where instead of taking it, squaring the differences and taking the square root power, what's the square root? How, in expressing it as a power, what do we raise something to take the square root? 1/2, right? So this is now the LK distance, where we take the difference between the kth coordinate, the ith coordinate, raise it to the kth power, and then take the square root of we sum those up over all dimensions, and then take the kth root of the whole thing. Okay? Any questions about it? It should be clear that replacing 2 by a different value of k yields a different notion of distance. Okay? And, there's certain values of k that are particularly famous. If we use k equals 1, what do we get if we use k equals 1? Manhattan distance. But what does that mean? We're summing up the difference between the coordinates, raising it to the 1th power, which does nothing, right? It's the sum of the and taking the 1th root of it does nothing, right? This says it's not just that every feature, you say, does this mean every feature merit is the same?
Differences in features don't get that. Like, if there's a square root, then the differences would matter. I'm sorry, if the differences are squared, right, then the distance matters. If you use, never mind.
What is the difference between the Manhattan distance and the Euclidean distance? Can this go negative? Well, there's an absolute value sign here. So there is no. See, that's an absolute value sign. So this can't go negative, right? Okay? But the question is really, what is it? And that was an articulate way to say we haven't quite got what that means, right? For k equals 1, what it really means is that the distance contribution is basically linear in each dimension, right? If we think about it, okay, let's compare it for the point 2, 0 and the point 1, 1, comparing that to the origin 0, 0. In the L1 distance, this is going to be a distance of 2. Does everybody see that? 1 plus 1 is 2. If we compare that in the L1 distance to a point 2, 0, the distance is going to be the sum of 2 plus 0, or 2. According to the L1 distance, both these points are equally far from the origin, right? According to the L2 distance, which one of these is closer to the origin? 1, 1, right? So it has to do with, the issue is really whether a small change in, whether we charge more for big changes than the sum of an equal amount of little changes. That's, I guess, the way that I would be putting it, what the difference is. For L1, 2 little changes were worth the same as 1 big change, right? For L2 distances, Euclidean distances, we weighed bigger changes more, right? There was a nonlinearity there, okay? Any questions? And another special case is the L infinity distance. What happens if we sum up the differences of each dimension, raise it to the infinitieth power, and then take the infinitieth root over that? Let's think what that means. Suppose I have something of the form, let's say my difference components were 1, 2. When I raise 1, let's make it 1.5 just to make it simpler. When I raise 1.5 to the infinitieth power, comparing that to 2 to the infinitieth power, are they going to be close or are they going to be far apart? Well, let's not think about it. What happens if I raise, right now, 1.5. What's 1.5 to the 1,000th? That's big. But compare it to 2 to the 1,000th. Okay? How much bigger is this? Okay? This is massively bigger than that. Okay? I mean, what would the difference be? The difference would be, when we subtract this from this, what do we get? This is going to be very, very tiny compared to that. Okay? And I'm not saying this without too much conviction here, but let's see one we can figure out. Okay? Certainly, if this was 1, let's just take a look at this. If we agree this is 1, 1 to the 1,000th was 1, right? 2 to the 1,000th is ungodly big, right? What is ungodly big minus 1? Ungodly big and hardly changed, right? Even if at 1.5 or 1.9, okay, the difference, this minus this, is going to be very, very close to that, okay? And what this argues, if you believe that, and again, you work out some examples to convince you, but basically if we sum it up over all different dimensions, if k is very, 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 very big, this sum is almost certainly going to reflect only the biggest difference between them, the single dimension where they have the biggest difference. And if we take the 1,000,000th root of that thing, all the other dimensions will have collapsed and been lost. Basically, this turns out to give you the maximum distance between in any one dimension. When you say, what's the root for? What do you mean, what's the root for?
What does it do?
Well, it takes the square root of the root of the number. But I mean, again, so to a certain extent, I'm not being straight. What was it for in the distance function? Okay, you're used to seeing this. You saw this in high school. Okay, what was it for there? Okay, it is a way of normalizing distances, and this is what, Euclid came up with. I don't know if Euclid came up with it or not, but frankly, this is not an unusual, this is how we are used to distances being computed. Okay, and the claim is that the important thing is that if you switch to the LK distance, all of these things happen to be metrics for all k. That's why this class of functions is interesting. In fact, one way to maybe say, why do we have the kth root in there? If we didn't have the kth root in here, it wouldn't be a distance metric. So we wouldn't have some of the properties that we have come to love, like the triangle inequality. Wouldn't hold. Okay? Yeah.
So for L1, even small changes are equivalent to making any big change. But in case of L2, small changes are penal.
In the case of, the way to think about it is in case of a L1, a bunch of small changes is the same as one big change of that magnitude. In the case of L2, it's not quite true, but it's still reasonably balanced between lots of little changes and a few big changes. As k gets bigger and bigger, eventually it gets to the point where it will ignore everything except the single dimension of biggest change. Any questions?
How do we laterally compute for k equal to infinity?
Okay, how do you compute for k equals infinity? How do you take the kth root of raise something to the kth power? This is something you use logarithms for and things like this. Okay? So the answer is saying, is there so the special case of the infinitieth power, okay, is there a button for infinity on your calculator? The answer is no. Okay? But there is a button for a large number. Okay? You can type in a large number, right? And then taking the kth root of this thing is simply a trick you did with logarithms and things like that. Okay? You could take a large number, or if someone says it's infinite, because we know that in the limit it's going to be the maximum component, the convention is, if someone wanted to take the L infinity distance, all they would do is find what is the largest difference. And they wouldn't actually compute raise it to any power, or it's what is the largest dimensional difference. Any questions? So what is the point of this? The important point of what the distance metric is, that when you have 2 points, okay, and you ask which one of these is closer to the origin, The answer is not, oh, it's this, it's not that. It says it depends upon your distance metric. Okay, according to your the L1 distance and L2 distance, it would say that P2 was closer to the origin. For the L infinity distance, this one, okay, actually, wait, I'm not sure I got this backwards. Oh, wait, which is farther, right, which is farther from it, right? Does everybody agree that according to, if these are the distances according to k equals 1, the farther point was P2, P2, P1? Okay? Any questions about it? Okay? And a way to think about this, when you're trying to, which value of k is the better one, the right one for you to be using? Note that it depends upon whether or not you're interested in, more worried, I would say, about random noise, or are you worried about artifacts? This is the way I would think about it. Suppose I measure, properties of people. If I measure them on a noisy scale, right? Does everybody kind of see that there's going to be a certain amount of difference between the actual value and, it would be x plus some noise, right? If I measured you with a noisy scale, there's going to be a certain amount of noise in each dimension, right? And if I have that kind of thing, it might be that what I'm really interested in, what are the relatively few dimensions where there is a really big difference between the two things? If so, I might be looking at a, something like an L infinity, something with a high power to it. If, on the other hand, I was worried that there was an error, an artifact measurement, that one of these measurements was really bad, do you see that if I have a L infinity type distance, I'm going to clue on what is the one dimension where they are most different, right? And so if there were reasons why there were artifacts, certain measurements that were extremely bad, I would be badly served by having a high power of k here, okay? Because that's what I'm going to think. It's purely this artifact is what I'm going to use to make the decision of how far apart we are. Any questions about that? So picking the right value of k here is an important thing, okay? And it has to do with really what do you view in some sense as being points that are neighbors, that are of equal distance apart from each other. So one thing that these different distance metrics define are different circles. What is a circle? We're used to saying, if I said which one of these is a circle, you would say, that's it, I see, that's a circle. What is a circle? A circle is defined as the set of points that are equal distance from the origin, right? Now, in an L2 world, which we are used to living in, this is what a circle looks like. In Manhattan, what does a circle look like? If I have to say, where can I walk to in 10 minutes? I can walk 10 minutes up this block, I can walk 10 minutes in that block, or I can walk 5 minutes in that block and 5 minutes on that block. Does everybody see that? This is a circle in L1 world. This is a circle in L2 world. This is a circle in L5 world. Okay? Does everybody see it's still rounded off? Maybe this is like Steve Jobs, I think, would like this kind of circle, right? Because it's a rounded rectangle type of, square type of thing, right? For an L infinity distance, it says that how far apart is this point? Well, this point here, there's some difference in the x and some difference in the y. The difference in the x doesn't matter because the y dominates it. Does everybody see that? Here the y is the dominant dimension. Here the x is the dominant dimension. We get that axis-aligned square. Any questions? So when you choose your distance, it's really going to be what are the points that you think should be equal distance from the origin. Any questions? Okay. Okay, what else can I say about, in a few minutes, about nearest neighbor methods? One thing that I can say is that, when you've got a high-dimensional data set, like you guys often have, finding the distance between high-dimensional data sets. Distances are kind of weird when we look at high dimensions, okay? You guys are used to living in three-dimensional world, and you know have an intuition about three dimensions. You don't have an intuition about 56 dimensions. And, you know, there's some strange things that happen in higher dimensions, okay, at least of our intuition, particularly relative to things like the size of spheres and the boxes that enclose them, okay? That if we think about what does a circle in 2 dimensions look like? Does everybody see that, right? If we look at the box that encloses it, it looks like this. Does the sphere fill up most of that box? You say yes, right? Now you do this game in 3 dimensions. And you put the marble in the box, right? Does the marble fill most of the box? You say yeah. What if we go to 8 dimensions, 10 dimensions, 100 dimensions? The answer is it fills a smaller and smaller percentage of the box. What's a one-dimensional sphere look like? Well, actually, it would just be a line segment, actually. Okay, in a line segment, what's a one-dimensional box? Okay, so the box and the sphere, this is perfectly. It turns out as you get higher and higher dimensions, the ratio of these things gets less and less, and so this lends weird things about dimensions as we get higher and higher into dimensions. But what I would say is, in a world where we feel comfortable in smaller dimensions, notice that if we do something like SVD, which took a large feature vector in a large number of dimensions and reduced it to a small number of components, so we had a small dimensional representation of it, finding the nearest neighbor